Hi everyone. Today I'm going to be taking you through my proof of the fixed point theorem, which states that if we have a continuous function from AB onto AB, then there exists a C element of the interval AB such that f of C equals C. I'm going to take you through my intuition of the proof, how I went about solving it, and kind of show you how I wrote it up rigorously. Then I'm going to show you how an AI agent, or ChatGPT in this case, also went about solving the proof. We're going to talk a little bit about the importance of the skills from proof writing and also the importance of human judgment when it comes to using artificial intelligence in mathematics.
So our theorem, let f be a continuous function from AB onto AB. Then there exists a C element of the interval AB such that f of C equals C. This is how we kind of rigorously state the fixed point theorem. And like all proofs, I want to start with the simplest idea in the proof, and that really is just like, what is a fixed point? So I drew this line, f of x equals x, also known as the identity function. But really what this is, it's just a line, and every single point on this line is a fixed point. I then compared this line to the line x plus 1. And the line x plus 1, what it does is it takes every x and it adds 1 to it. So obviously, this line is never going to have a fixed point. Next, I looked at another function that you may be familiar with, f of x equals e to the x, that also does not have a fixed point. And kind of intuitively, when x is positive, e to the x grows much faster than our line f of x equals x, and then it's also never going to be negative because of the way exponentials work. So this is why we never have a fixed point. Now, I kind of observed a function that does have a fixed point. This function f of x equals x squared. And you can see kind of visually here is that where it has a fixed point, it's going to intersect our line f of x equals x. Another point that does this is our sine function here. This is sine of x plus 1. You can see there the little intersection is a fixed point. So the next thing that I did was I introduced a box. Because the other important part of the theorem is that the function is bounded from AB to AB, meaning that it lives with entirely within a box of length and width A to B. I chose just 0 to 2 on the x-axis, 0 to 2 on the y-axis to make the visual work. However, we can choose any arbitrary number. As we can see, from 0 to 2, our sine function, sine x plus 1, lives entirely within this box. And we can also see that there's a fixed point within the box. And before the fixed point, the sine function is entirely above the line, f of x equals x. And then after the fixed point, which is entirely below the line. And because it's a continuous function, it cannot skip over the fixed point, so it has to have its fixed point at the intersection. So kind of expanding on this idea is I drew two arbitrary cubics. You can see the green cubic lives entirely within the box, and you can see the red cubic starts in the box, but then it grows very quickly and leaves the box. The red cubic here does not have a fixed point. And the green cubic here, which lives entirely within the box, does have a fixed point. And the idea being is that at some point, it has to be above the line f of x equals x, and then at some point it's going to be below the line f of x equals x, and that the intersection there has to exist because the green cubic here is a continuous function. So what I wanted to do was I wanted to look at the behavior, meaning where does the function switch behavior from being strictly greater than the line f of x equals x, and then being strictly less than the line f of x equals x. So I think we can kind of see visually that when a function lives entirely within a square box, or a function is from A to B onto A to B, that we are going to have a fixed point. And while that visual is fantastic for building intuition and maybe gives you a starting point for how to prove it, it's not sufficient in an actual mathematical proof, which has to be done rigorously. So the way I did that is I took the upper half of our box, including the diagonal that cuts through at the line f of x equals x, and I called that a set. So I defined that set to be S equals the set of all x's element of AB, such that f of x is greater than or equal to x. And then I had to define some things about the set that are going to be useful for later. For example, I had to show that the set was not empty, because we can talk all we want about the properties of an element of a set. Set itself is empty. That kind of becomes a useless argument. Also, I showed that set is bounded, meaning that it doesn't go off infinitely. And then we say by completeness, let C equal the supremum of S. And all completeness means is that our set isn't missing like a key part of it. If you have a number line of all the numbers, every number that's supposed to be on that number line is there. For example, if we have 1, 2, 3, 4, 5, the set of integers, we're missing 2, that set wouldn't be complete. And then we said that this point C is the supremum, and all that means is that C is the smallest upper bound of set S. And what an upper bound is we just say that nothing is going to be above that S. So we are going to proceed by showing that f of C equals C, or the supremum of our set, is a fixed point by contradiction. And what this means is that we assume what we want to show is not true, and then we show that if that holds, there's some violation of a mathematical rule. So we start by supposing, we're going to do this in two cases. We start by supposing that f of C is greater than C. And so then we're going to choose a y that is greater than C and less than f of C. And choosing this y, what that's going to allow us to do is it's going to allow us to show that there is an x that is in the set S that is also greater than C, which is a contradiction because C, being the supremum of S, is an upper bound of S. So x cannot simultaneously be in the set S and then also greater than C. So therefore, f of C cannot be greater than C. Now we're moving on to case 2. And just like case 1, I'm just going to show you the idea of this, and we're not going to get super specific about what each individual part of the proof is actually saying. So we start by supposing that f of C is less than C. And what that means is that we can choose a y that's greater than f of C and less than C. Now, we want to show that, well, we know that C is an acclamation point of the set S because C is the supremum of S. And what that means is there's an infinite amount of points close to C and S. Or if you choose any positive distance, there is at least one point at most that distance away from C in S. So if C is greater than f of C, then that point lies below the diagonal that we created before. So it lies below the line f of x equals x. And if it lies below the line f of x equals x, then there's a positive distance between that point and the line. That means is we can choose a point. We can choose a point that is between C and between the line f of x equals x, and then that point has to be in the set S, which doesn't make any sense because it violates our rule for the set S, which is f of x has to be greater than or equal to x, but we found a point such that f of x is less than x. So this is also a contradiction. So since we found two contradictions, we've shown that f of C cannot be greater than C and f of C cannot be less than C, we can conclude that f of C must equal C via continuity, thus f has a fixed point in AB. Now I'm going to take you through the AI's proof of the theorem. It starts by defining a new function g of x such that g of x equals f of x minus x. And it says that since f of x and the identity function x are continuous, that the composition of them are also continuous, which is a true statement. And then it observes that f of a is greater than or equal to a, and f of b is less than or equal to b, which is also true, and that this will imply that g of a, which equals f of a minus a, is greater than or equal to 0, and that g of b, which equals f of b minus b, is less than or equal to 0. So, assuming that none of the endpoints are fixed points, which would just prove our theorem, this means that g of a is greater than 0 and g of b is less than 0. Since g is continuous on AB, we can use the intermediate value theorem. And what this states is that for an interval AB, if we have the function, a continuous function on this interval, must take every single value between f of a and f of b. So this means since g of A is greater than 0 and g of B is less than 0, there must be some g of C that equals 0 on the interval AB. Thus, there's some f of C minus C that equals 0, and so f of C then has to equal C. And thus, f has a fixed point in AB. And everything in this proof is true. So this is a trustworthy proof that you would be able to use to solve.
So that was AI's proof of the fixed point theorem. And I will say, in a lot of ways, that the proof is better than mine. It's faster, it's more clear. And that's something that's really important in math. You want to be able to explain things as quickly and as clearly as possible to other people. However, I'm still really glad that I went about proving the theorem the way that I did, because I feel like that I personally learned about math. I grew my intuition a little bit. I was able to become better at applying that intuition rigorously. I think that's something that's really important, the learning process. When you ask AI to just answer a question, it'll give you the answer. And you'll be able to learn how to answer that one question, but you probably will not be able to generalize. And I've heard this idea called the productive struggle. When we sit down with a problem and we struggle with it and we attack it from all different types of angles, we come up with creative solutions. That is probably the best way to learn something, to actually just sit down and think about it. And I think that's something that we lose with AI. We lose some of that creativity. We lose that productive struggle because it is so easy to just go ask AI to show you something. And I think that even if you don't care about learning, I don't think that's a fun way to go about life. I don't think it's interesting to, whenever you need to make a thought, whenever you need to think about anything, you just ask AI and it does all of your thinking for you. I think that's kind of a shallow existence. And you might ask, oh, why do you care? AI is going to take our job. It's going to be able to do math. It's going to be able to do computer science. It's going to be able to do everything. And that might be true. I mean, I'm not an expert on the field, but even if that is true, we're still going to need human judgment. We're still going to need people to verify AI's results, to apply the results that it comes up with. So at the very least, you should grow your judgment, because you should be able to verify if things are true or if things are false, and not to take everything at face value. And finally, you might be asking, why would I even care? Why would I care that an AI can write a math proof better than me? I'm not a mathematician. Why would I even care to learn a math proof? It's so impractical. When am I ever going to use real analysis? And in a lot of ways, that might be true. You know, if you're not a mathematician, if you're going into a completely different field, writing a proof isn't something that is inherently useful to you. However, the skills that you learn from it are, because the skills of a proof are really just making a clear and logical argument, which is useful no matter what field or really in just everyday life. If you can speak with people and speak in a clear, logical way, that will help your social skills. If you are a writer and you can't write in a logical or clear manner, you're not going to be a very good writer. You're not going to be a good biologist. You're not going to be a good paleontologist, right? You should be able to express your ideas clearly and logically. And I think if you take anything away from this video, that is what I want you to take away, is the ability to express yourself in a way that makes sense to other people. I hope you enjoyed. I hope you found my proof interesting, maybe learned something, and have a great day.